In this video, we are going to take a look at the analytic approach to computing limits at infinity. So computing these limits without looking at tables of numbers or looking at the graphs of the functions involved. One thing to note is all of the limit laws that we covered for limits as x goes to a number, as x goes to a, let's say, all of those limit laws and facts hold for limits at infinity. What we're going to do to compute limits of functions just analytically here is to look at the limits of the power functions. So for instance, the power functions are functions that are of the form x to some number power. So here, the limit as x goes to infinity of the function x, if I just look at that function, that's what that function looks like, and as I go far off to the right, the graph of f of x equals x just goes up. As I go far off to the left here, the graph of f of x just goes down. So it is a straight line with slope 1, right? That goes through the origin. So here we would say the limit as x goes to infinity of x equals positive infinity. The farther you go off to the right, as x goes to infinity, right, so does x here. And as x goes to negative infinity, so does x here. So all right. The next power function that we'll look at is x squared, right? And so as x goes to infinity, remember the limit laws are valid here, right? And in this case, if we look at x squared, and let's just take a look at the graph of it really quickly. Right, the graph of f of x equals x squared looks like that. So as I go far off to the right on this function, this graph just goes up here, and as I go far off to the left with this function, this graph also goes up. And so the limit, what we would say in terms of the limits at infinity, right, the limit as x goes to infinity of x squared would be positive infinity, and the limit as x goes to negative infinity of x squared is also positive infinity. So what we'll notice here is that there will be sort of a trend with the odd exponents power function and the even exponent power functions. Here, the limit as x goes to infinity of x to some odd number power will be infinity. In fact, even number powers also. But the limit as x goes to negative infinity, if I have an odd power right here, right, then I will wind up with a negative infinity. And if the power is even, right, then, right, any number, especially a negative number, right, raised to an even power will also be positive. So all of the y values on the left side, if for an even power, will be positive. So there's no choice but for the even power functions to go off to infinity. So if I look at the next power function, x cubed, I can see that the limit as x goes to infinity of x cubed is infinity, right? So that's no surprise. I have positive numbers, and they're getting really big. When I raise them to the third power, the result will be even bigger, right? So the limit as x goes to infinity of x cubed is infinity. And here, the limit as x goes to negative infinity of x to the third, well, 3 is an odd power, right? So if I plug a really big negative number in here, a really small negative number, and raise it to the third power, right, negative 1 raised to the third power is also going to be negative 1. So here we'll have negative infinity. For x to the fourth, that's an even power, right? And so on both sides, and the limit as x goes to infinity and the limit as x goes to negative infinity of both of those will be positive infinity. And that pattern just continues. For the odd powers, the limit as x goes to infinity will be positive infinity. The limit as x goes to negative infinity will be negative infinity. And for the even powers, they will be infinity on both sides. Okay. All right. We can generalize this a little bit to positive real numbers. If r is a positive real number, then the limit as x goes to infinity of x to any positive real number power is also going to be infinity. So that could be any number, not just whole numbers or odd or even. So the limit as x goes to infinity of x to the square root 2 power. Square root 2 is a positive real number, so that would be infinity. If r is a positive rational number, such that x to the r is a real number for any real number x, then the limit as x goes to minus infinity of x to the r is minus infinity. That's about the best that we can say. And just as an example here, let's take a look at an example of this one. If I had the limit as x goes to infinity of the square root of x, right? The square root of x can be rewritten as x to the 1/2 power, right? That's any of these radicals can be represented as a fractional exponent. And so here we would be in this situation here, right? The limit as x goes to infinity of x to the 1/2. 1/2's a positive real number, so that limit would be infinity. Here we have the limit as x goes to negative infinity of the cube root of x. Okay, so the cube root, being an odd root, has no issues with taking the cube root of a negative number. So that's sort of what they're alluding to right here. If x to the r is a real number for any real number x. So that wouldn't be true for, say, like x to the 1/2. So we couldn't even really take the limit as x goes to negative infinity of x to the 1/2 in this class. We would just kind of avoid that, because a negative number raised to the 1/2 power, or the square root of a negative number, would be a complex number, which this class doesn't deal with. So here the limit as x goes to negative infinity of x to the 1/3 is going to be negative infinity here. So this type we wouldn't even worry about taking the limit as x goes to infinity, or negative infinity, sorry. All right, here are some more power functions, and these would be power functions where the x is down in the bottom. You could rewrite these as x to some number power. The exponent would be negative on these here, and these are pretty easy to deal with, because they're all going to be 0 no matter what, if x is even, or the power on x is even or odd. So looking at 1 over x, let's just take a look at the graph of that to kind of, that's what the graph would look like. And so the farther I go off, right, to the right over here, you can see the closer and closer this graph gets to the x-axis. In other words, the closer the y values get to 0. Same thing over here. The closer and closer these values get to 0. So the limit as x goes to infinity of 1 over x would be 0. The limit as x goes to negative infinity of 1 over x would be 0. And nothing really is going to change too much in terms of the limit. If I look at 1 over x squared, I still get the same situation where the limit as x goes to infinity is 0. The graph gets closer and closer to the x-axis. Same thing over here. So for these power functions, it doesn't really matter what the power is. There's 0 on both sides if you look at those. So we're really going to rely on these facts and the other facts about power functions to compute limits as x goes to infinity of more complicated functions. In general, we can say the following facts. And if r is any positive real number, then the limit as x goes to infinity of 1 over x to the r is 0. And for the other direction, the limit as x goes to negative infinity, we would need to make sure that x to the r is a real number for any real number x. So again, sort of the same situation that we had before. 2 examples of that would be the limit as x goes to infinity of 1 over square root x, which would be the same as 1 over x to the 1/2 power. That would be, that's typo there, both of those should be 0. So this should be 0 here, and this should be 0 here. Okay. Okay, so that's it for this. Now what we're going to do in the next section is use those facts that we had in this section about the power functions to compute some limits at infinity.